But also material, monetary, other sort of constraints. They differ from ongoing activities in that they tend to be one-shot packages of activities. They may be repeated with variations, but if a project gets repeated continuously, it's no longer a project in the sense it's now just part of the general operations of the organization. So what we wanted to do is predict whether a project was likely to be successful or unsuccessful using some of the big data techniques that exist now, well, two in particular. And projects, as we know, are constrained by several factors such as their time and their scope and their cost. And the typical joke is that you can have maybe two of those attributes satisfied, or sometimes one, or of course sometimes none of those attributes satisfied simultaneously. But you're not going to get all three of them satisfied simultaneously, so your job will be to find yourself somewhere in the middle, a satisfied point, which will get the scope and cost and time within reasonable constraints. So the way in which he phrased his research objectives was sort of in a sort of pseudo-formula way. So if you look at the dissertation itself, I don't think I included that much of it in the paper, but basically he wants to come up with a function which will take a set of projects and give you an outcome. It's basically a binary classification problem because all it attempts to answer is the question is, does it think this project will be successful, yes or no? Now, just because something is a binary classification problem doesn't necessarily mean that it's a simple problem. So if you think of something like a court case or whatever, the outcome might be guilty or not guilty, but the decision process behind it can be fairly complicated. So that's that first line there. The next one is you need some method given a set of projects that are sort of structurally similar, which will give you this function. So this isn't really a mathematical function in a sense. It's just basically we needed to come up with an approach with how we could analyze a historical set of projects to give us this predictor, which will give us this outcome. And then lastly, we dealt with an issue of data, which I think might be one of the weak points in this study, is that it became really difficult to find companies who were willing to give us data on their project success rates, yes or no, which was really unfortunate because my student has a great job at a consulting firm which is very international and deals with this data all the time, and I was hoping that because of his connections there he might be able to get some of this data, but they were completely unwilling to part with it. And since I haven't named the company, I was really hoping they would do it because it's turned out in the South African press at least that this company is less than ethical and is willing to bend the rules for other people, but not for me, so that's unfortunate. So nonetheless, we had to make an alternative arrangement for how to generate data for this study, and what we eventually wound up doing was the sort of high-level descriptive statistics of successful projects published by one of the rivals to his company, KPMG. This isn't KPMG, the rival is. And we used that study to create a generator of pseudo-projects, which we used just as a proof of concept for the system. Although it would have been much better to have real data, although this synthesized data was grounded in a study based in reality, it would have been much better to have had outright realistic data. So these were the research questions for his projects. I was basically just, I've sort of summarized them by reading the formulas to you, but one of the approaches that we can use to represent projects in a way that's suitable for a machine learning approach, such as, well, the one we wound up using at the end was neuroevolution. The absence of this historic data was a huge problem, so we needed to come up with a reasonably sound framework for generating projects that match the descriptions of successful projects and unsuccessful projects to train this system so that it could be deployed. And then the final high-level outcome is, at the end of the day, could we use such an approach to forecast the outcome of a project. So the outcome, as I said before, is simply a yes/no answer, a hot dog, not hot dog. It's not trying to give you a spread for how much you think a budget overrun would be or a time overrun. Simply a yes/no answer for whether it thought it would be successful. So the approach used in the research was to first come up with the various hypotheses. Then we followed a prototype-driven approach to the research. So we developed the core system itself, which went through several iterations, testing and refinements. And I'll discuss with you one major problem that came out of the initial version of the system, which we were able to re-architect by adding an additional layer of learning on top of it, which seems to get it to an okay-ish level of performance. And then eventually the end results of the research were the prototype system itself, which was an implementation of the abstract model that he defined. We'll discuss the various components of the system and its models as we go forward. So the overall approach towards approaching the solution. How did the students get to the final endpoint? So at the end of the day, what we got was a high-level framework or methodology, an approach to representing projects. So projects themselves are defined in all sorts of terrible human-readable formats, documents, WhatsApp chats, all sorts of very difficult to nail down. So obviously we can't deal with that nicely. So wouldn't it be nice if there was a sort of more mathematically tractable representation for projects? In this case, projects as a series of vectors in an overall matrix representing a set of projects. This we based on the KPMG study, which is referenced in the article itself. And then once you've got your data in a meaningful format, what can you do with it? Well, we wanted the classifier itself to be a neural network approach, but the problems with neural networks, as we'll go forward, is that there's a lot, and it's true with all machine learning approaches, that there's a bit of art to the science. There's a lot of decisions that need to be made, which have huge consequences to the efficacy of the final solution. And we're trying to automate as many of those decision processes as possible to take out more of the variables. At the end of the day, there still has to be humans in the loop to pick the right parameters or hyperparameters or hyperparameters, whatever you want to call it, but we wanted an approach that at least would have some degree of automation to it, and it spits out as its end product the actual predictor. So that was the methodology that was used, and the actual implementation of that methodology he referred to as synergy, which also included as its project representation phase the generator of what he referred to as pseudo-projects, the data set which matches the descriptions of the KPMG study. And from that point on, it's much the same. The neuroevolution system produces the predictors, which then can be tested for their accuracy. So, because we wanted to keep this machine readable and useful as inputs to the neural network, a matrix representation was constructed based on the information study, which basically tracked aspects like the amount of support as a numerical value. Now, of course, there's hidden, just because something's numbers doesn't mean that something is not subjective at all. How do you measure things like strong sponsor support and urgency and so on? All of those have various fluffy human baggage associated with them. But that is the KPMG study's problem, not our problem. So they acted as the filter for our system. So we assume that this is gold standard truth, and that became the basis for our data set. So the overall approach to learning is we want to use the historical data for the pseudo-historical data for the generated data set. and then generalize from those examples to create a predictor at the end of the day, and then once it's presented with new projects, it will give an indication as to whether those projects would be successful, yes or no, based on the historic data it had seen up until that point. So that basically falls under the overall ambit of supervised learning, with the proviso that the data itself was generated. So we've got a labeled training set where we know the outcomes of the historical projects. We're trying to create a function, although that function will be represented as the weights inside a neural network rather than an explicit formula, such that when we present it with new data, we'll be able to get a result, yes or no, as to whether the project should be successful. So the same discussion, just basically in pseudocode. For the approach, it does mention over here bootstrapping, which we'll get to a bit later, because as it turned out, the initial approach, which was just a simple neural network architecture and a simple genetic algorithm, didn't work very well, although it worked not too badly that it couldn't be fixed. So we will discuss that when we get to it. The overall high-level approach to one aspect of the learning was the evolutionary algorithm, of which there are many specific variations. But in general, the evolutionary algorithms will generate a whole bunch of candidate solutions and then evaluate them for how well they satisfy the problem. So as a sort of meta approach to problem solving, you're definitely not guaranteed to get the best results, but given enough time and suitable parameters that you've chosen, you might get satisfactory results. So optimization, I've always thought, is a bit of a strong term for evolutionary algorithms, because they're not going to give you any guarantees, but they will give you something satisfying after a while, assuming that they converge. So they generate the candidate solutions, which will be stored in a pool of population. They will be evaluated for their fitness and then diversified with various operations. Those operations could be mutation, where individual candidate solutions are modified, or they could be by combining candidate solutions in the pool, so that ostensibly positive aspects of one candidate solution will be transferred to the next generation, and over time the overall fitness of the population will improve, and that cycle is repeated until either you give up and are satisfied with the best answers you've seen so far, or it converges to a point where your criteria have been met and you can end the cycle. So a bit more detailed than that high-level approach was that we did a generational approach to neural networks. And so we generate the population, we evaluate all the members of the population, we select parents, which are called the crossover operation. They'll be selected according to their fitness and combined. The underlying representation of candidate solutions in the pool is just a binary string. So it's simply a string concatenation operation, picking a random crossover point. And then mutation, where in proportion to how poorly the solutions are performing, they stand a greater chance of being modified randomly, just in the hopes that it will sort of shake the overall system out of a local minimum if it's been stuck in that local minimum or something like that. And then to keep the population stable, the weakest members of the population will be replaced by those stronger offspring, and that process will continue until the termination condition is met, which can include, as I said, just running out of time. So for selection of parents, the particular approach that was used is called roulette wheel selection, but basically you can think of it as fitness proportional selection. So the quality of the solution determines how likely it is to be selected for crossover. So the better it is, the larger area on an imaginary roulette wheel it occupies, and the chances of it being selected are therefore much higher. You don't actually have to implement that as a virtual roulette wheel, which means that there's a relationship between the fitness of the solution and its likelihood of being selected. In terms of the actual crossover approaches, we tried two. One is simply where we sort the populations according to their fitness and then take the best two. And the others is where you divide it into a series of tournaments and take the winners of each of those tournaments until eventually you come down to two candidates for crossover. Now again, these little decisions about what crossover approach to use and what selection approach to use, and if you're doing tournament selection, how many tournaments there are, they all boil down to us. So at the end of the day, we took a neural network approach, which is a very simple multi-layered perceptron network, and fed in the historical data that we generated. The historical generator we matched to the descriptive statistics using a test which basically shows how likely a random population is to be a subpopulation of the larger population. And the overall architecture looked like this. Now, another decision that you have to make is how many layers you want between the input layer, where each of the features of the projects are fed in, and the output layer, which represents whether it's successful or not. There's no exact science to that. The student did find a formula in the literature for working out what should be reasonable, but I can't say how good that was. At the end of the day, did it work? Yes, but not that well. So we got about a 57% accuracy, which is better than half, so that's not terrible, but it's also not great. So we fixed it, and the way that we fixed it is we fixed it with something called Bootstrap Aggregation or bagging. So the basic idea is we don't know which aspects of the data set are more important than others, so we randomly select subsets of the data with replacements. So it's possible to overemphasize other aspects of the data set and then train it on those modified data sets. And that lifted the overall accuracy from 57% up to, on average, I think it was 74 or 5, about 80% accuracy. So is it good? I don't know. In the terms of classification problems, they'll typically show you things of like 90% accuracy and so on. But I think there's a lot of confounding variables that aren't being measured by that KPMG study. So things like I don't think all of the things that they measure are actually predicting the success or failure of projects. So it was successful in that sense, that it was better than the version without ensemble learning, and both of those were predictors, although the first version was what we call a weak predictor rather than a strong predictor.